Hello and welcome. I'm so glad you're here with me tonight. Find a comfortable position wherever you are. Let your shoulders drop, release any tension you might be holding in your jaw, and take a slow, deep breath. Hold it for just a moment, then now let it go. Tonight we're going on a journey together, a peaceful exploration into one of the most beautiful and fundamental concepts in all of mathematics. We're going to discover how polynomials, these elegant mathematical expressions, are woven into the very fabric of our universe. But don't worry if mathematics hasn't always been your favorite subject. Tonight there are no tests, no pressure, no rushing. We're simply going to wander through ideas together, at a pace that feels calm and natural. Think of this time as a gift you're giving yourself, a chance to let your mind drift through the cosmos of mathematical thought, to see patterns and connections that have been hiding in plain sight all along. Mathematics at its heart isn't about memorizing formulas or solving problems under pressure. It's about discovering a language that describes everything around us. From the arc of a thrown ball to the orbit of distant planets, from the growth of populations to the decay of radioactive elements, from the curves of a flower petal to the waves of sound that carry music to our ears. And at the center of all of this, quietly holding so much of the universe together, are polynomials. Now, you might be wondering, what exactly is a polynomial? The word itself sounds technical, perhaps even intimidating. But I promise you, by the time our journey ends tonight, you'll see polynomials not as abstract symbols on a page, as old friends, companions that have been with humanity for thousands of years, helping us understand and describe the world. In the simplest terms, a polynomial is just an expression made up of variables and coefficients, combined using addition, subtraction, and multiplication. Something like x squared plus 3 times plus 2, or 5y cubed minus 2y plus 7. These might look simple, but within these expressions lies extraordinary power. The power to model the flight of rockets, to predict the behavior of economies, to encode secret messages, to design the curves of bridges and buildings, to process the images on your phone, and to unlock countless other mysteries of our universe. Tonight we'll explore why polynomials are so special. We'll talk about their history, stretching back to ancient Babylon and Egypt. We'll discover how they appear everywhere in nature. We'll understand why they're the secret language that connects algebra, geometry, and calculus. We'll see how they help us solve problems that seem impossibly complex. And we'll learn how modern technology, from the internet to artificial intelligence, relies on polynomials in ways you might never have imagined. But most importantly, we'll do all of this together, gently and calmly. There's no rush. Let each idea settle in your mind like snowflakes landing on still water. If your thoughts wander, that's perfectly fine. Let them drift, and then gently come back when you're ready. So take another deep breath with me now. In and out. Feel yourself settling into this moment. The universe is vast, but right now, in this space, we're going to explore one of its most elegant secrets. Let's begin. Part 1. The Ancient Origins. Where polynomials were born. To truly appreciate polynomials, we need to travel back in time. Close your eyes for a moment, and imagine yourself transported to ancient Mesopotamia, nearly 4,000 years ago. The sun is warm, the air smells of irrigation canals and clay, and you're standing in a school, what the Babylonians called in Hujuba, the tablet house. The Babylonians were master problem solvers. They needed to be. They had to measure fields for planting, calculate taxes, predict flooding, and build structures. And to do all of this, they developed sophisticated mathematics. On clay tablets that archaeologists have discovered, we can see that the Babylonians were solving what we would now call polynomial equations, particularly quadratic equations, those involving x squared. One famous tablet, known as YBC 72089, shows that the Babylonians could calculate square roots with remarkable accuracy. Another set of tablets shows them solving problems like, I have a square plot of land. I increased one side by 7 units and the other by 3 units, and the area increased by 96 square units. What were the original dimensions? Think about what's happening here. They're working with expressions involving x and x squared, polynomials, and they're doing it centuries before the Greeks and millennia before modern algebra would develop. Now let's drift forward in time, to ancient Egypt. Picture the Nile River, its annual flooding depositing rich soil that made Egypt the breadbasket of the ancient world. The Egyptians needed to resurvey their fields after each flood, and this practical need drove their mathematical development. In the Rhine Papyrus, dating to around 1650, we find Egyptian scribes working through problems that involve what we now recognize as linear and quadratic polynomials. They didn't have our modern notation, no x's or y's or equal signs, but the underlying mathematical reasoning was there. encoded in their heretic script. Feel the weight of time here. For thousands of years, across different cultures and civilizations, humans have been drawn to these mathematical patterns. Polynomials weren't invented by one person, or discovered all at once. They emerged naturally from humanity's need to understand quantity, space, and change. Let's continue our journey, drifting now to ancient Greece. Here, mathematics took on a different character. The Greeks, particularly the Pythagoreans, saw mathematics as a path to understanding ultimate reality. Numbers weren't just practical tools. They were mystical, divine, the language of the cosmos itself. Euclid's Elements, written around 300 BCE, is one of the most influential mathematical texts ever created. In it, Euclid presents geometry with rigorous logical proofs. But interestingly, many of the geometric theorems in Euclid can be reinterpreted as statements about polynomials. When Euclid talks about cutting a line segment into two parts, such that the rectangle formed by the whole line and one part equals the square of the other part, he's actually describing what we would now write as the quadratic equation x squared equals a multiplied by the difference of a and x. The Greeks preferred geometry to algebra, but the mathematics they were doing, the relationships they were exploring, were fundamentally polynomial in nature. As we move through time, we come to the Islamic Golden Age, roughly from the 8th to the 14th centuries. This was a period of extraordinary mathematical development. The great scholar Al-Khwarizmi, working in Baghdad around 820 CE, wrote a book whose title gave us the word algebra, meaning the reunion of broken parts. Al-Khwarizmi systematically explained how to solve quadratic equations. He gave geometric proofs, showed how to complete the squared, and classified different types of problems. His work, and that of other Islamic mathematicians like Omar Khayyam, yes, the same Omar Khayyam who wrote the beautiful poetry of the Rubaiyat, pushed polynomial mathematics forward in profound ways. Omar Khayyam, in particular, worked on cubic equations, polynomials involving x cubed. These are significantly more challenging than quadratics, and Khayyam developed geometric methods for solving them using conic sections. Imagine a Persian polymath, known today mostly for his poetry about wine and roses, was actually one of the greatest mathematicians of his age, unlocking secrets of cubic polynomials. Let's pause here for a moment and just breathe. Feel the continuity of human thought across these centuries. From Babylonian clay tablets to Egyptian papyrus, from Greek geometric proofs to Islamic algebraic treatises, the thread of polynomial mathematics runs through civilization like a golden thread through fabric. Now, as we drift into Renaissance Europe, something remarkable happens. Mathematics begins to accelerate. Italian mathematicians in the 16th century, Scipione del Ferro, Niccolò Tartaglia, Girolamo Cardano, and Lodovico Ferrari, achieve what had seemed impossible. They find general formulas for solving cubic and quartic equations. This was revolutionary. For quadratic equations, we have the quadratic formula. You might remember it, though there's no need to recall it now. But cubic and quartic formulas are much more complex. The story of their discovery involves drama, secret methods, broken promises, and public challenges, all the intrigue of the Renaissance era. But here's what's truly beautiful. These mathematicians were uncovering universal truths. The formulas they found weren't just clever tricks. They revealed deep structures in the mathematical universe. Every cubic polynomial has a certain character, a certain behavior, governed by these formulas. It's as if the mathematicians were archaeologists, carefully brushing away sand, to reveal the architecture of mathematical reality that had always been there, waiting. Then, in 1824, a young Norwegian mathematician named Niels Henrik Abel proved something shocking. There is no general formula for solving polynomial equations of degree 5 or higher. No formula at all. This doesn't mean such equations can't be solved. Many can. But there's no single universal formula like the quadratic formula. Shortly after, a brilliant but troubled young French mathematician named Évariste Galois, on the night before a duel that would kill him at age 20, wrote down his mathematical insights in a fevered letter. His work established group theory and explained exactly which polynomial equations could be solved by formulas and which couldn't. Galois' mathematics was so ahead of its time that it took decades for others to fully understand it. Take a deep breath. Feel the passion of these mathematicians, the late nights, and fierce dedication, the beauty they saw in these abstract patterns. The development of polynomial mathematics is a testament to human curiosity and creativity. From ancient problems about land measurement to modern abstract algebra, polynomials have been constant companions on humanity's mathematical journey. Part 2. The nature of polynomials. Understanding the fundamentals. Now that we've traveled through history, let's settle into a deeper understanding of what polynomials actually are. Think of this section as sitting down with an old friend and really getting to know them, their personality, their quirks, what makes them special. At the most basic level, a polynomial is an expression built from variables and constants using only addition, subtraction, and multiplication. The variable is usually written as x, though it could be any letter. The constants are numbers, coefficients that multiply the variables, and a constant term that stands alone. I'll rewrite this entire document converting all the mathematical symbols into words, matching the document's contemplative lyrical style. Here's a simple example. 3x squared plus 5x minus 2. This is a polynomial. It has three terms. The first term, 3x squared, has a coefficient of 3, and the variable is squared. The second term, 5x, has a coefficient of 5, and the variable to the first power. The third term, negative 2, is just a constant. The degree of a polynomial is the highest power of the variable that appears. In our example, the highest power is 2, so this is a second-degree polynomial, or a quadratic. Now, let's just breathe with that for a moment. There's something deeply satisfying about it, the structure of polynomials. They're orderly. They follow rules. Yet within these rules, there's infinite variety. A first-degree polynomial looks like a times x plus b, just a straight line. Simple, elegant, direct. It tells you that as x increases, the value increases at a constant rate. This is the mathematics of steady change, of linear relationships. If you're paid by the hour, the relationship between hours worked and money earned is first-degree polynomial, linear. A second-degree polynomial, the quadratic, looks like a times x squared plus b times x plus c. Now things get more interesting. The graph of the quadratic is a parabola, that beautiful U-shaped or inverted U-shaped curve. Parabolas appear everywhere in nature. When you throw a ball, it traces a parabolic path. The cables of a suspension bridge, when hanging under their own weight, approximate a parabola. Satellite dishes are parabolic, because this shape focuses incoming waves to a single point. Feel the elegance of this. The simple expression, just x squared, describes curved motion, describes shapes in nature, describes the focusing of light and radio waves. Third-degree polynomials, cubics, have the form a times x cubed plus b times x squared plus c times x plus d. Their graphs have an S-like shape, with possible local maxima and minima, hills and valleys. Cubics can model more complex phenomena, things that grow, reach a maximum, then decrease, or that have inflection points where the nature of change itself changes. As we go to higher degrees, quartix x to the fourth power, quintix x to the fifth power, and beyond, the polynomials can model increasingly complex behaviors. But here's something wonderful. No matter how complex they get, polynomials maintain a certain character. They're smooth, no sudden jumps or breaks. They're continuous. You can draw them without lifting your pen. They're differentiable. You can calculate their rate of change at any point. This smoothness, this well-behaved nature, is part of why polynomials are so useful. They're complex enough to model real phenomena, but simple enough to work with mathematically. Let me share something that might seem magical at first. Every polynomial can be factored into linear terms, at least if we allow complex numbers. This is called the fundamental theorem of algebra, and it was proved by Carl Friedrich Gauss in 1799, when he was just 22 years old. What this means is that any polynomial can be broken down into simpler pieces. A quadratic like x squared minus 5x plus 6 factors into the quantity x minus 2 times the quantity x minus 3. A cubic like x cubed minus 6x squared plus 11x minus 6 factors into the quantity x minus 1 times the quantity x minus 2 times the quantity x minus 3. The roots of the polynomial, the values where it equals 0, are these factors, 1, 2, and 3. Breathe with this idea. Even the most complicated polynomial is really just the product of simple linear factors. It's like how a complex molecule is built from simple atoms, or how a symphony is built from individual notes. There's a beautiful reductionism here, a way that complexity emerges from simplicity. Now here's another profound property. Polynomials are closed under addition and multiplication. What does this mean? It means if you add two polynomials, you get another polynomial. You multiply two polynomials, you get another polynomial. They form what mathematicians call a ring, a structure with both addition and multiplication that follows certain rules. This might sound abstract, but it's deeply important. It means polynomials form a self-contained mathematical universe. You can work within the world of polynomials, combining and manipulating them in various ways, and you never leave that world. You never suddenly get something that's not a polynomial. Well, unless you divide, division can give you rational functions, which are ratios of polynomials. But multiplication and addition always stay within the family. Let's talk about something else beautiful. The relationship between polynomials and symmetry. Consider a polynomial like x squared minus 4. It factors as the quantity x minus 2 times the quantity x plus 2. Notice the symmetry? The roots are 2 and negative 2, perfectly balanced around 0. The graph of this polynomial is symmetric around the y-axis. In general, even degree terms, x squared, x to the 4th power, x to the 6th power, create symmetry, while odd degree terms, x cubed, x to the 5th power, create antisymmetry. A polynomial made entirely of even degree terms has a graph that's symmetric. The left side mirrors the right. A polynomial made entirely of odd degree terms has a graph with rotational symmetry. If you rotate it 180 degrees around the origin, it looks the same. This connection between the algebraic structure, even and odd powers, and the geometric structure, symmetry of the graph, is one of mathematics' beautiful harmonies. The symbolic and the visual speak the same language. Take a moment to let your mind rind. Perhaps imagine these polynomials as curves in space, each with its own character, its own pattern of hills and valleys, its own symmetries and behaviors. They're like musical phrases, each with its own melody. One more fundamental property before we move on. Polynomials are determined by their values. If you know the value of a polynomial at enough points, you can reconstruct the entire polynomial. Specifically, a polynomial of degree n is completely determined by its values, at n plus 1 distinct points. This is called Lagrange interpolation, after Joseph Louis Lagrange. It means that if you have a quadratic polynomial, and you know its value at 3 points, you can figure out what the polynomial is. If you have a cubic, and you know its value at 4 points, you can determine it exactly. This property has profound implications. It means polynomials can be used to fit data, to pass curves through points, to interpolate between known values. It's one reason why polynomials are so useful in applied mathematics. They can approximate complex functions, fit experimental data, and model real-world phenomena. Imagine this. You have measurements at certain points, and you want to estimate values in between. A polynomial can thread through your data points like a smooth curve through beads on a string. It honors your known values while giving you a reasonable guess for the unknowns. This is the essence of polynomial interpolation, and it's used everywhere. In computer graphics to create smooth curves, in numerical analysis to approximate functions, in signal processing to reconstruct signals from samples. Let's rest here for a moment. Feel the fundamental nature of what we've explored. Polynomials are expressions of variables and coefficients. They have degrees that determine their basic character. They can be factored into roots. They form a closed mathematical structure. They embody symmetry. They can interpolate and approximate. These aren't just abstract properties. Each one opens a door to applications, to understanding, to solving problems. Polynomials are foundational because they're simple enough to understand, yet rich enough to be useful. They're the bridge between pure mathematics and applied science. Part 3. Polynomials in the natural world. The universe's language. Now, let's step outside, metaphorically speaking. Let's look at the world around us and see where polynomials appear in nature. You might be surprised by how ubiquitous they are. Start with something simple. The path of a thrown object. When you toss a ball, it follows a parabolic arc, the graph of a quadratic polynomial. This is because of gravity. The horizontal position changes linearly with time, constant velocity, while the vertical position changes quadratically, constant acceleration. The equation describing a falling object looks something like this. The height at any moment equals the starting height, plus the initial upward velocity multiplied by time, minus half of the gravitational acceleration, multiplied by time squared. That part, about half the gravitational acceleration times time squared, the quadratic term, is what creates the characteristic parabolic shape that describes how objects actually fall. Every thrown ball, every fountain of water, every basketball shot, traces this curve. Athletes intuitively understand this polynomial, even if they've never studied algebra. They've internalized the mathematics through practice, through feel. Breathe into this realization. The flight of birds, the trajectory of projectiles, the arc of water from a hose, all governed by this simple quadratic relationship. When Johannes Kepler analyzed Tycho Brahe's meticulous observations of Mars, he made a stunning discovery. Planets don't orbit in perfect circles. They trace ellipses instead. These elliptical paths can be expressed mathematically by taking the horizontal distance squared, dividing it by 1 radius, then adding the vertical distance squared, dividing by 1 radius. And when you do this correctly, the result always equals 1. Those 2 radii are what mathematicians call the semi-major axis and the semi-minor axis, describing the ellipse's long and short dimensions. Later, Isaac Newton showed that elliptical orbits are a natural consequence of gravity, following an inverse square law. The mathematics of planetary motion is deeply polynomial, involving squared terms in distance and velocity. Every planet in our solar system, every moon, every asteroid, follows a path described by polynomial equations. The entire celestial dance above us is choreographed by polynomial mathematics. Consider also the vibrations of a string or a drumhead. When a guitar string vibrates, it forms standing waves. The fundamental frequency and overtones, the harmonics that give each instrument its unique sound, are related to polynomial equations. The normal modes of vibration are solutions to polynomial eigenvalue problems. The music you hear, the timbre that distinguishes a violin from a flute, emerges from polynomial mathematics describing how objects vibrate. Let's think about growth and decay. Many natural processes follow polynomial patterns, at least approximately or over certain ranges. Population growth, radioactive decay, the spread of diseases, chemical reactions. These often involve polynomial relationships. A simple model of population growth might work like this. The population at any time equals the starting population, plus a constant growth rate multiplied by time, plus another factor multiplied by time squared. The first part gives you the initial population you started with. The second part represents steady, constant growth, the population increasing at a fixed rate. The third part, with time squared, captures how that growth might speed up or slow down as conditions change. Of course, real natural processes are usually more complex, involving exponentials and logarithms and other functions. But polynomials often provide excellent approximations over limited ranges. They're like the first words of a language, not capturing every nuance, but getting a main idea across. Think about the structure of crystals. The arrangements of atoms in crystalline solids involve symmetries that are described by polynomial equations. The energy states of electrons in atoms and molecules are solutions to polynomial equations arising from quantum mechanics. At the deepest level, the Schrödinger equation, the fundamental equation of quantum mechanics, often reduces to polynomial problems when solving for energy levels. The hydrogen atom, that simplest and most important quantum system, has energy levels that come from solving polynomial equations. So the very structure of quantum matter, the arrangement of electrons that gives each element its chemical properties, involves polynomial mathematics. Let's turn to biology. The shape of shells, the arrangement of petals in a flower, the branching patterns of trees, these often follow mathematical patterns. While not always exactly polynomial, they can often be approximated or described using polynomial functions. The spiral of a nautilus shell, for instance, follows a logarithmic spiral, but can be approximated by polynomial curves and limited sections. The growth patterns of plants, the way leaves arrange themselves to maximize sunlight, the Fibonacci sequences appearing in pine cones and sunflowers, all of these have connections to polynomial mathematics. Take a deep breath. Feel how mathematics weaves through nature, describing motion, structure, growth, vibration, the behavior of matter and energy. Even the shape of raindrops is determined by polynomial equations. Small drops are roughly spherical, but larger drops flatten out. Their shape determined by the balance between surface tension and air resistance. The balance described by fluid dynamics equations that are fundamentally polynomial in nature. The ripples spreading out when a stone hits water, the formation of snowflakes, the patterns in sand dunes, the distribution of prime numbers, the structure of DNA, the folding of proteins. At some level, in some way, polynomial mathematics helps describe all of these. This isn't to say polynomials explain everything. The universe is far too rich for that. But polynomials are one of the fundamental tools, one of the basic languages, that mathematics uses to describe reality. Here's something profound to consider. Why do polynomials appear so often in nature? One reason is that they represent the simplest forms of smooth change. A constant term represents a static quantity. A linear term represents constant change. A quadratic term represents constant acceleration, change in the rate of change. A cubic represents constant jerk, change in acceleration. Nature often operates through these kinds of layered changes. Position changes to create velocity. Velocity changes to create acceleration. Acceleration changes to create jerk. Each layer adds a degree to the polynomial. So polynomials naturally arise whenever we have quantities changing over time, through forces that remain relatively constant, or through processes that build up through multiple layers of influence. There's something almost philosophical here. Polynomials are simple enough to emerge naturally from basic physical laws, yet complex enough to create rich, diverse behaviors. They occupy a sweet spot in mathematical complexity, the zone where simplicity meets expressiveness. Let your mind rest on this idea. The universe could have been structured in infinitely many ways, following infinitely many types of mathematical laws. But the laws that actually govern our universe, gravity, electromagnetism, quantum mechanics, lead naturally to polynomial mathematics. Is this a coincidence? Or does it suggest something deep about the relationship between mathematics and physical reality? These are questions that have fascinated philosophers and physicists for centuries, questions that remain open, inviting contemplation. Part 4. Polynomials and Calculus. The mathematics of change. Now we're going to gently explore one of the most beautiful connections in all of mathematics, the relationship between polynomials and calculus. If you've studied calculus, you'll see familiar ideas in a new light. If you haven't, don't worry. We'll approach this intuitively, focusing on the big ideas rather than technical details. Calculus is the mathematics of change. It asks questions like, how fast is something changing? How can we find maximum and minimum values? How can we calculate areas and volumes of complex shapes? And polynomials, it turns out, are the perfect training ground for calculus. Let's start with the derivative, which measures the rate of change. If you have a function that describes position over time, the derivative tells you velocity. If you have a function for velocity, its derivative gives you acceleration. Here's what makes polynomials so elegant. Calculating their derivatives is remarkably straightforward. Take any term like x to some power. To find its derivative, you bring the power down in front as a multiplier, and then reduce the power by 1. So x squared becomes 2x, x cubed becomes 3x squared. If you start with 5x to the fourth power, its derivative is 20x cubed. The pattern is simple, consistent, and always works the same way. This simplicity is profound. It means we can easily find rates of change for any polynomial function. We can locate maxima and minima by finding where the derivative equals 0. We can analyze how functions increase and decrease, accelerate and decelerate. Think about what this means practically. Engineers designing a roller coaster need to know where the steepest parts are, where riders will experience the most force. Economists modeling markets need to find equilibrium points where supply equals demand. Physicists analyzing motion need to find when objects reach maximum height or velocity. Polynomials, because their derivatives are so easy to work with, provide tractable models for all these situations. Now, integration, the reverse of differentiation, is almost as simple. Integrating a polynomial means increasing each power by 1 and dividing by the new power. The integral of x squared is x cubed divided by 3. The integral of x cubed is x by x by x by x divided 4. Integration lets us calculate areas under curves, accumulated quantities, total distances from velocities. Again, the simplicity of polynomial integration makes these calculations feasible. Here's something remarkable. Every polynomial is infinitely differentiable. You can take the derivative once, twice, 3 times as many times as you want. Each time you differentiate a polynomial, you get another polynomial of lower degree. Eventually, you reach 0, but you never get something undefined or problematic. This smoothness, this infinite differentiability, makes polynomials ideal for calculus. They're well behaved in every way that matters for analysis. But here's where things get even more interesting. Polynomials can approximate other functions. This is one of their most powerful applications. Imagine you have a complicated function, maybe a trigonometric function, like sine or cosine, maybe an exponential function, maybe something defined by a complex physical process. These functions might be difficult to work with directly, but you can approximate them using polynomials. This is the idea behind Taylor's series and Maclaurin series, named after Brooke Taylor and Colin Maclaurin. Any smooth function can be represented as an infinite sum of polynomial terms. For example, the sine function can be written as sin equals x, x3, 6, plus x5, 120, times 7, 5, 40, plus. Even just taking the first few terms gives you a pretty good approximation near x equals 0. Take more terms, and the approximation gets better. Let this sink in for a moment. Polynomials can approximate any smooth function. They're like the fundamental building blocks from which all other functions can be constructed, at least approximately. Your calculator, when it computes sine or cosine, or logarithm, is actually using polynomial approximations. The computer chips doing the calculations work with polynomials, because they're simple enough to compute quickly, but accurate enough to give good results. This is part of why we say polynomials are the secret to mathematics. They're not just interesting in themselves, they're the key to understanding and approximating everything else. Another beautiful application comes from the fundamental theorem of calculus, which connects differentiation and integration. This theorem says that differentiation and integration are inverse operations. One undoes the other. For polynomials, this relationship is transparent and beautiful. Every time you differentiate, you can integrate back to recover the original polynomial, plus a constant. The mathematics is clean and symmetric. This symmetry, this balance between rates of change and accumulation, between derivatives and integrals, is one of the deep harmonies of mathematics, and it's most clearly visible in the behavior of polynomials. Let's think about optimization problems. Suppose you want to maximize something, profit, efficiency, happiness, whatever. If you can model your situation with a polynomial function, finding the maximum is straightforward. Take the derivative, set it equal to 0, solve for the critical points, check which one gives the maximum value. Countless real-world problems are solved this way. Businesses optimize pricing. Engineers optimize designs. Scientists optimize experimental parameters. And very often, the underlying mathematics involves polynomial functions and their derivatives. Consider also differential equations. Equations involving derivatives. These arise whenever we have quantities that depend on their own rates of change. Population models where growth rate depends on current population. Physical systems where acceleration depends on position. Economic models where change in prices depends on current prices. Many differential equations involve polynomials, or can be solved using polynomial techniques. The simplest differential equations have polynomial solutions. More complex ones can often be approximated by polynomials. Take a moment to breathe and reflect. Calculus, this powerful tool for understanding change and accumulation, works so smoothly with polynomials. It's as if they were made for each other, and in a sense they were. The development of calculus by Newton and Leibniz was intimately connected with understanding polynomials and their behavior. There's something almost miraculous about how everything fits together. Polynomials describe natural phenomena. They're simple to differentiate and integrate. They can approximate other functions. They solve optimization problems. They appear in differential equations. It's as if the universe designed polynomials to be the perfect mathematical tool. Simple enough to work with. Powerful enough to model reality. Rich enough to reward deep study. Part 5. Polynomials and Modern Technology. The digital world. Now let's make a gentle transition from the natural world and pure mathematics to modern technology. You might not realize it, but polynomials are working behind the scenes in almost every piece of technology you use. Your phone, your computer, the internet, streaming video, digital photography, GPS, medical imaging, all of these rely on polynomial mathematics. Let's start with something you might not expect. Error correcting codes. Whenever you send data over the internet, stream a video, or use a QR code, errors can occur. Bits can flip from 1 to 0, or vice versa. Noise in communication channels can corrupt data. But remarkably, the data usually arrives intact. How? Error correcting codes, many of which are based on polynomials. One famous example is Reed-Solomon codes, used in CDs, DVDs, QR codes, and deep space communication. These codes represent data as polynomials. By adding redundancy, extra terms to the polynomial, the codes can detect and correct errors. The mathematics is elegant. You encode your message as coefficients of a polynomial, evaluate the polynomial at several points, and transmit these values. Even if some values get corrupted during transmission, you can recover the original polynomial through interpolation, as long as enough values come through correctly. This is the same polynomial interpolation we mentioned earlier, but now used in a completely practical, modern context. The mathematics that Lagrange studied in the 18th century enables your ability to watch Netflix today. Take a breath and appreciate this connection across centuries. Pure mathematics, studied for its own beauty, becomes the foundation of everyday technology. Now let's think about computer graphics. When you see smooth curves of surfaces on a screen, in video games, animated movies, CAD designs, fonts, these are usually represented by polynomial curves called splines. Bezier curves, named after Pierre Bézier, use polynomials to create smooth curves that can be easily controlled. You specify a few control points, and the polynomial curve bends to pass through or near these points, creating pleasing smooth shapes. Every font on your computer, every letter you type is defined by polynomial curves. The smooth outline of an S, or the curve of an O, is described by piecewise polynomial functions. In 3D graphics, polynomial surfaces extend this to 3 dimensions, creating the smooth skins of characters in animated films, or the curved bodies of cars in design software. The reason polynomials work so well for this is their smoothness and controllability. By adjusting control points, designers can intuitively shape curves. By using piecewise polynomials, different polynomials for different segments, you can create curves of arbitrary complexity while maintaining smoothness at the joints. Let's talk about signal processing. Sound, images, and video are all signals, functions that vary over time or space. Processing these signals, filtering out noise, compressing for storage, analyzing for patterns, often involves polynomial techniques. The fast Fourier transform FFT, one of the most important algorithms in all of computing, can be understood through polynomial mathematics. It efficiently computes how a signal can be represented as a sum of simple waves, sines and cosines. The mathematics involves evaluating polynomials at special points called roots of unity. The FFT makes possible everything from digital music, to medical imaging, MRI and CT scans, to analyzing astronomical data. And at its heart, it's polynomial mathematics. Image compression. The algorithms that make JPEG images smaller, that let you store thousands of photos on your phone, also uses polynomial techniques. The discrete cosine transform, central to JPEG compression, is related to polynomial approximation. Think about your GPS. It receives signals from satellites and calculates your position. The calculations involve solving polynomial equations, finding the intersection of spheres defined by the distances to different satellites. These are systems of polynomial equations. Machine learning and artificial intelligence also use polynomials extensively. Neural networks, which have revolutionized AI in recent years, often use polynomial activation functions. When training these networks, we're essentially finding the coefficients of very high-dimensional polynomials that best fit the training data. Support vector machines, another machine learning technique, use polynomial kernels to classify data. By mapping data into higher dimensional spaces, using polynomial transformations, these algorithms can find complex patterns. Let's think about cryptography, the mathematics of keeping information secret. Many modern encryption schemes rely on the difficulty of factoring large polynomials over finite fields. RSA encryption, though usually described in terms of integer factoring, can be reformulated using polynomial mathematics. The elliptic curve cryptography, increasingly used for secure communication, involves polynomial equations of a special type. The security of your online banking, your encrypted messages, your digital signatures, all rest on polynomial mathematics. Consider also robotics. When a robot arm needs to move from one position to another, it follows a trajectory. This trajectory is planned using polynomial functions that ensure smooth motion, respecting constraints on velocity and acceleration. Polynomial path planning ensures robots move efficiently and safely, whether they're assembling cars in factories or performing surgery in operating rooms. In finance, polynomial models are used to price options and other derivatives. The Black-Scholes equation, perhaps the most famous equation in quantitative finance, can be solved using polynomial techniques under certain conditions. Even weather forecasting relies on polynomial mathematics. The equations governing atmospheric motion, fluid dynamics, thermodynamics, are often solved numerically using polynomial approximations. The weather forecast you check on your phone comes from massive computations involving polynomials. Take a moment to let this wash over you. Almost every aspect of modern technological life touches polynomial mathematics. From the moment you wake up and check your phone, through your day of communication and computation, to the entertainment you enjoy in the evening, polynomials are there, working quietly in the background. This ubiquity isn't accidental. Polynomials occupy that sweet spot we mentioned earlier, simple enough to compute efficiently, expressive enough to model complex phenomena, well understood enough that we know their properties and limitations. Engineers and computer scientists turn to polynomials again and again because they work. They're the reliable, trustworthy tools that bridge theoretical mathematics and practical technology. And here's something beautiful to contemplate. The mathematics hasn't changed. The polynomials defined by ancient Babylonians, studied by Renaissance algebraists, analyzed by 18th century mathematicians. These are the same polynomials powering 21st century technology. Mathematics is eternal in this way. Discoveries don't become obsolete. The truths uncovered by mathematicians centuries ago remain true, waiting to be applied in new contexts to solve new problems. So, when you use your phone, remember, you're touching mathematics that has been part of human understanding for millennia, now given new life in silicon and software. The deeper patterns, polynomials, and abstract mathematics. We're entering the final stretch of our journey now. Let's gently ascend to a more abstract view, looking at how polynomials fit into the larger structure of mathematics. Don't worry if some of these ideas feel distant or theoretical. Just let them drift through your mind like clouds. In higher mathematics, polynomials are studied as objects in themselves, divorced from any particular application. Mathematicians ask, what are the essential properties of polynomials? How do they relate to other mathematical structures? What patterns and symmetries do they embody? Polynomials have a special mathematical property. They form what's called a ring. This just means you can add polynomials together and get another polynomial. You can multiply polynomials together and get another polynomial, and these operations behave predictably according to familiar rules. When you're working specifically with polynomials that have real number coefficients, regular numbers like 2 or 3 or negative 5.7, mathematicians give this collection a name, R, the join X, which means the ring of all polynomials in X with real coefficients. This might sound abstract, but it's actually liberating. By thinking of polynomials as elements of a ring, mathematicians can apply general theorems about rings to understand polynomial behavior. For instance, polynomials form what's called a unique factorization domain, meaning every polynomial can be factored into irreducible polynomials in essentially one way, just as every integer can be factored into primes in essentially one way. This is a deep structural property. There's also the study of polynomial rings over different fields. If instead of real numbers you use rational numbers, or complex numbers, or even finite fields, where arithmetic wraps around, you get different polynomial rings with different properties. Polynomials over finite fields are particularly important in modern applications. In computer science and coding theory, working modulo a prime number creates a finite field, and polynomials over these fields have special properties useful for error correction, cryptography, and algorithm design. Let's talk about ideals, another abstract concept. An ideal in a ring is a subset that's closed under addition and multiplication by ring elements. In polynomial rings, ideals correspond to geometric objects. This connection between algebraic ideals and geometric varieties is the foundation of algebraic geometry, one of the deepest areas of modern mathematics. The idea is roughly this. A polynomial equation like x squared plus y squared equals 1 defines a circle in the plane. The polynomial x squared plus y squared minus 1 generates what mathematicians call an ideal, and this ideal corresponds to the circle. Different ideals correspond to different geometric shapes. This correspondence lets mathematicians translate between algebra and geometry, using each to illuminate the other. It's one of the great unifying themes of mathematics, that different areas of math are really talking about the same things in different languages. Breathe into this unity. Mathematics, despite appearing fragmented into specialized areas, is deeply interconnected. Polynomials are one of the threads binding it together. Consider also the concept of a polynomial function versus a polynomial expression. This might seem like splitting hairs, but there's a subtle difference. A polynomial expression is a formal symbol, like 3x squared plus 2x plus 1. A polynomial function is what you get when you evaluate this expression at different hex values, actually plugging in numbers and seeing what comes out. Over infinite fields like the reals, these are essentially the same. Different polynomial expressions give different functions. But over finite fields, different expressions can give the same function. These subtleties matter in abstract algebra and computational complexity theory. Let's touch on Galois theory, which we mentioned briefly earlier. This beautiful theory, developed by Évariste Galois, studies the symmetries of polynomial equations. The key insight is that you can associate a group, another algebraic structure to each polynomial, and this group encodes information about the polynomial's solvability. For quadratic, cubic, and quartic polynomials, the associated groups have special properties that allow the equations to be solved by radicals, by formulas involving nth roots. For quintic and higher degree polynomials, the groups are more complicated, and in general, no such formulas exist. This is one of mathematics' profound achievements, taking a concrete problem, solving polynomial equations, and revealing its deep connection to abstract group theory. The impossibility of solving the quintic isn't just a practical limitation, it's a fundamental truth about the structure of symmetry. Polynomials also connect to linear algebra, the study of vectors and matrices. The characteristic polynomial of a matrix encodes information about the matrix's eigenvalues, special values that determine the matrix's behavior. These eigenvalues appear in countless applications, from quantum mechanics to Google's PageRank algorithm. The Cayley-Hamilton theorem states that every matrix satisfies its own characteristic polynomial. This is a beautiful bridge between polynomials and linear algebra. In functional analysis, which studies infinite-dimensional polynomials, appear as dense subsets. The Weierstrass approximation theorem states that polynomials are dense in the space of continuous functions, meaning any continuous function can be approximated arbitrarily well by polynomials. This is a rigorous version of what we discussed earlier about Taylor series. It says that polynomials, despite being simple objects, are rich enough to approximate any continuous function you can imagine. Let's consider orthogonal polynomials, families of polynomials that are perpendicular to each other in a certain sense. Examples include Legendre polynomials, Chebyshev polynomials, and Hermite polynomials. These appear in solutions to differential equations, in quantum mechanics, in approximation theory, in numerical integration. Each family has special properties tailored to particular applications. Chebyshev polynomials, for instance, minimize the maximum error when approximating functions, making them ideal for certain numerical computations. These orthogonal polynomials aren't artificial constructions. They arise naturally from physical problems. Legendre polynomials come from solving Laplace's equation in spherical coordinates. Hermite polynomials appear in the quantum harmonic oscillator. Mathematics discovers these patterns in nature and reveals their polynomial structure. Take a deep breath. We've journeyed into fairly abstract territory, but notice the recurring themes: unity, connection, pattern, structure. Polynomials aren't isolated objects. They're nodes in a vast network of mathematical relationships. Every area of mathematics, it seems, touches polynomials in some way, and polynomials in turn illuminate these areas, providing concrete examples, test cases, and bridges between theories. This is why we can say polynomials are the secret to mathematics. Not because they're the only important thing, but because they're a thread running through everything, connecting disparate ideas, grounding abstract theories, in concrete calculations. The philosophy of polynomials, what they tell us about reality. As we near the end of our journey, let's step back and ask some philosophical questions. What do polynomials tell us about the nature of mathematics? About reality? About the human mind? First, there's the question of mathematical realism versus constructivism. Are polynomials discovered or invented? When ancient mathematicians worked with quadratic equations, were they uncovering pre-existing truths or constructing useful tools? Polynomials seem to exist in some sense independent of humanity. The quadratic formula worked the same for Babylonians, for Islamic scholars, for Renaissance Europeans, and for modern students. It would work the same for alien civilizations, if they exist. This suggests mathematical realism, that mathematical truths exist independently, in some platonic realm, waiting to be discovered. Polynomials aren't arbitrary human creations, but objective features of what? Of logical structure? Of the universe itself? On the other hand, the particular way we write polynomials, the notation we use, the problems we choose to solve, these are human constructions. Different cultures develop different approaches. Our modern notation is a historical contingency, not inevitable. Perhaps the truth is somewhere in between. The patterns and relationships are real and objective, but the particular ways we describe and work with these patterns are human constructions, shaped by our cognitive abilities and cultural history. Let this question rest lightly in your mind. Is mathematics discovered or invented? It's a question that has puzzled philosophers for millennia, and polynomials sit right at the heart of it. Consider also the unreasonable effectiveness in mathematics, the phrase coined by physicist Eugene Wigner. Why does mathematics, developed often for purely aesthetic or intellectual reasons, turn out to be so useful in describing the physical world? Polynomials were studied initially as abstract equations. Only later did scientists realize they described projectile motion, planetary orbits, quantum energy levels. This happened again and again. Pure mathematics becoming applied science. Is this because the universe is fundamentally mathematical, or because mathematics is our way of finding patterns, and pattern finding is useful regardless of the universe's true nature? Perhaps polynomials are effective because they represent the simplest forms of relationships: direct proportionality, linear, squared relationships, quadratic, and so on. Then perhaps nature, following principles of simplicity or minimum action, tends toward these simple relationships. Or perhaps our minds are tuned to recognize polynomial-like patterns, because these patterns were evolutionarily useful. Our ancestors, who could intuitively grasp parabolic trajectories, better at hunting, survived better than those who couldn't. In this view, polynomials aren't special features of the universe, but special features of how our minds conceptualize the universe. We see polynomials everywhere, because we're wired to look for them, but this seems insufficient. Polynomials work in contexts far removed from human evolution, in quantum mechanics, in cosmology, in realms our ancestors never encountered. The effectiveness seems to go beyond evolutionary psychology. Breathe with these mysteries. They're profound questions without easy answers, but polynomials give them concrete form. Let's think about simplicity and complexity. Polynomials are among the simplest mathematical objects, just variables raised to powers, added together. Yet from this simplicity emerges enormous complexity. High-degree polynomials can have intricate behaviors, with many roots, many local maxima and minima, subtle patterns. Polynomial systems, multiple polynomials and multiple variables, can be extraordinarily complex, describing high-dimensional geometries. This emergence of complexity from simplicity is a recurring theme in mathematics and science. Simple rules produce complex behavior. Simple laws generate diverse phenomena. Polynomials exemplify this. They also exemplify universality, the idea that certain simple structures appear everywhere, because they're in some sense inevitable. Just as the number 0 appears in every mathematical system, just as certain symmetries appear in every physical theory, polynomials appear everywhere. Because they're fundamental. They're what you get when you allow the most basic operations, addition, multiplication on the most basic objects, numbers, variables. Given these operations, polynomials arise inevitably, and once they arise, they structure everything else. Consider the relationship between polynomials and other functions. We've mentioned how polynomials can approximate other functions, exponentials, trigonometric functions, whatever. In some sense, then, polynomials are more fundamental. Other functions can be understood as limits or generalizations of polynomials. The exponential function emerges as a limit of increasingly complex polynomials. Start with 1 plus x, then add x squared divided by 2, then add x cubed divided by 6. Keep adding more and more terms, each one a higher power of x divided by an appropriate number. As you add infinitely many of these terms, you approach the exponential function. Sine and cosine work the same way. They're limits of polynomial expressions with more and more terms. In this view, all the functions we encounter are really shadows or extensions of polynomials, as if polynomials are the fundamental building blocks underlying everything. Or think about it differently. In any local region, any smooth function looks like a polynomial. It's Taylor polynomial. Polynomials are the local reality. Other functions are just many polynomial pieces stitched together. This gives polynomials a kind of ontological priority. They're the building blocks from which mathematical reality is constructed. Take a moment to sit with this idea. In the vast landscape of mathematics, polynomials are foundational. Not the only foundation. Set theory, logic, number theory, all make their claims, but one of the essential foundations. Let's consider one more philosophical angle: the relationship between discrete and continuous. Polynomials bridge these realms. They're defined by discrete data, their coefficients, finite numbers. Yet they define continuous functions, smooth curves. A polynomial like x squared plus 3x minus 2 is completely determined by just 3 numbers: 1, 3, and -2. That's finite information, just 3 coefficients. Yet, from these 3 simple numbers emerges a continuous parabola, an infinite object in a sense, defined for every real number you could possibly choose for x. This discreteness giving rise to continuity, finiteness giving rise to infinity, is another profound mystery. Polynomials don't resolve the mystery, but they embody it in a particularly clear way. They also connect the algebraic and the geometric, symbolic manipulation and spatial intuition. When you factor a polynomial, you're doing algebra. When you graph it, you're doing geometry. The two perspectives complement each other, each illuminating what the other obscures. This duality, algebra and geometry, discrete and continuous, finite and infinite, is central to mathematics, and polynomials live right at the intersection. We've traveled far together tonight. From ancient clay tablets to modern computer chips, from projectile motion to quantum mechanics, from pure abstraction to practical application. Polynomials have been our thread through the tapestry of mathematics and reality. Let's gently gather up what we've learned and see how it all connects. Polynomials are expressions built from variables and constants using simple operations. This simplicity is deceptive. It masks profound depth. From the straightforward foundation, we can model natural phenomena, solve practical problems, develop advanced technology, and explore abstract mathematical structures. We've seen polynomials in history, emerging independently in different cultures, because they address fundamental questions about quantity and change. We've seen them in nature, describing the arc of a thrown ball, the orbit of planets, the vibration of strings, the structure of matter. We've explored how polynomials connect to calculus, serving as the perfect testbed for understanding derivatives and integrals, rates of change and accumulation. We've seen how they approximate other functions, making them versatile tools for analysis. We've discovered polynomials hiding inside modern technology, in error correction, computer graphics, signal processing, machine learning, cryptography. These ancient mathematical objects enable our digital world. We've ascended to abstract mathematics, seen how polynomials fit into ring theory, algebraic geometry, Galois theory, linear algebra. They're not isolated curiosities, but central threads connecting different areas of mathematics. And we've contemplated philosophical questions. Are polynomials discovered or invented? Why are they so effective at describing reality? What do they tell us about the relationship between simplicity and complexity, discrete and continuous, algebraic and geometric? Throughout this journey, certain themes have emerged. Let them settle in your mind now like sediment, drifting down through water. Universality. Polynomials appear everywhere, in every culture, every application, every area of mathematics. This isn't coincidence, but reflects something deep about their fundamental nature. Simplicity. Polynomials are built from the most basic operations. Yet this simplicity doesn't limit them. It empowers them, making them tractable while remaining expressive. Connection. Polynomials bridge different areas of mathematics and science. They connect algebra to geometry, discrete to continuous, pure to applied. They're a lingua franca of mathematics approximation. Polynomials can approximate more complex functions, making them tools for understanding the complicated through the simpler. Structure. Polynomials have rich internal structure, roots, factorizations, symmetries, degrees. Studying this structure reveals patterns in nature and in mathematics itself. Take a deep breath. Feel the weight of these realizations. Polynomials aren't just formulas to memorize or problems to solve. They're windows into the mathematical structure of reality. They're tools that humanity has honed over millennia. They're bridges between the abstract and the concrete, the simple and the complex. When you understand polynomials deeply, not just mechanically but conceptually, you understand something essential about how mathematics works, how science describes nature, how technology functions, how pure thought connects to physical reality. This is why we can say polynomials are the secret to the universe, or at least a secret, one of the essential keys. Not because they explain everything, no single concept could, but because they're so fundamental, so widely applicable, so deeply woven into the fabric of mathematical understanding. As you drift towards sleep tonight, let these ideas percolate through your mind. Picture parabolas and cubic curves, oscillating like gentle waves. Imagine ancient scholars bent over their tablets, Renaissance mathematicians in heated debate, modern computers humming as they evaluate polynomials millions of times per second. See the connections, from thrown stones to quantum mechanics, from simple equations to deep theorems, from human curiosity to technological revolution. Feel how mathematics weaves through reality, and how polynomials are one of the strongest threads in that weaving. You're part of this story too. Every time you've solved a quadratic equation, graphed a parabola, or wondered about the path of a ball, you've touched this deep mathematics. You've connected with insights that span millennia and bridge cultures. Mathematics isn't distant or cold or irrelevant. It's the language of pattern and structure, of change and constancy, of simplicity and complexity. And polynomials are one of the first words of that language, simple enough to learn, profound enough to study for a lifetime. As you close your eyes now and let sleep come, know that the universe is mathematical in ways we're still discovering. The patterns we've explored tonight, polynomial patterns, are just the beginning. There's always more to understand, more to appreciate, more connections to make. But for now, rest. Let your mind relax, release the details, and simply hold on to the wonder of it all. Mathematics surrounds us, describes us, enables our technology, structures our understanding. And polynomials, those elegant expressions of variables and coefficients, are quietly essential to it all. Thank you for journeying with me tonight through this mathematical landscape. May your dreams be filled with smooth curves and elegant patterns, with the quiet satisfaction of understanding something deep and beautiful about the cosmos we inhabit. Sleep well. The mathematics will still be there tomorrow, waiting for us to explore further, to discover more, to continue humanity's eternal conversation with the structures underlying reality. The secret to the universe isn't hidden in some distant realm. It's right here in the mathematics we can understand and appreciate, in the graceful curves of polynomials, in the patterns they reveal, in the connections they enable. The Polynomial Revolution, How Nature Speaks in Curves. Hello again, friend. Welcome back to our continuing journey through the mathematical universe. I'm so glad you're here with me as we settle in for what might be one of the most beautiful explorations we've undertaken together. Tonight, we're going to talk about something that changed everything. We're going to talk about polynomials, that I promise you, by the time we finish, you'll understand why they might just be the closest thing mathematics has to the secret of the universe itself. Before we dive in, I want you to get comfortable. Maybe grab a warm drink if you like. Find yourself in a cozy spot where your mind can wander freely through these ideas. What we're about to explore together isn't just mathematics in the sterile sense that you might have learned it in a classroom. This is mathematics as a language, as a way of understanding the fundamental rhythms that govern everything around us. You see, polynomials are everywhere. They're in the curve of a bridge, in the trajectory of a thrown ball, in the way plants grow, in the expansion of the universe itself. They're humble, in a way. They don't announce themselves with fanfare. But once you understand what they really are, you start seeing them everywhere, and the world becomes a far more elegant place. Let me start with a simple question that might seem almost too basic. What is a polynomial? Really? Well, at its heart, a polynomial is just a sum of terms. Each term is made up of a number multiplied by a variable raised to some power. I know that sounds abstract, so let me make it real for you. Imagine you're standing in a garden, and you're watching how a plant grows over time. On the first day, the plant is a certain height. On the second day, it's a little taller. On the third day, even taller still. You decide to write down a rule that describes this growth. You might say something like, the height equals 1 foot plus 1.5 inches times the number of days plus a tiny bit of extra growth for each day squared. That sentence I just spoke, that's a polynomial. When a mathematician writes it in symbols, they write something like, height equals 1 plus 1.5 times d plus 0.01 times d squared. But the story is the same whether I tell it in words or symbols. What we're really saying is that the height depends on the days in a very particular way. It's not just linear, it's not just straight upward. It has this curved quality to it, this acceleration. That's what the squared part gives us. It's the poetry of growth. Now, here's where it gets really interesting. A polynomial is fundamentally a way of building complex behavior from simple pieces. Each term is simple. Multiply a number by a variable raised to a power. That's straightforward. But when you add them together, something magical happens. You can create curves that are smooth, that flow, that capture the essence of how things actually happen in the real world. The history of polynomials is really the history of humanity learning to describe the world mathematically. For thousands of years, people worked with them without always knowing they were doing so. Ancient builders used curved arches in their buildings. These arches follow parabolic shapes, which are just polynomials of degree 2. Architects didn't sit down and calculate polynomials exactly. They found shapes that worked, shapes that distributed weight beautifully, shapes that had strength and elegance. But when mathematics developed further, when people like René Descartes, and later Isaac Newton, and Gottfried Leibniz came along, they realized that all these curves, all these patterns in nature, could be described using polynomials. This was revolutionary. It meant you didn't have to guess at designs or fumble through trial and error. You could calculate them. You could predict how things would behave before you built them. Let me tell you about the structure of a polynomial, in a way that feels almost musical. Think of a polynomial as a melody. The lowest power term is like the bass note, the foundation. The highest power term is like the soaring melody at the top. Everything in between fills in the middle ranges, creating texture and depth. The simplest polynomial is called a constant. It's just a number, all by itself. Imagine saying, the temperature is 72 degrees. That's not really changing. It's constant. In polynomial terms, that would be a polynomial of degree 0. There's no variable, no change. It's just what it is. Next we have what's called a linear polynomial. This is where we introduce the variable for the first time. Imagine the temperature increases by 3 degrees every hour. So after 1 hour, it's 75 degrees. After 2 hours, 78. The rule would be, the temperature equals 72, plus 3 times the number of hours elapsed. That's linear. It's called degree 1 because the highest power of the variable is 1. The graph of this relationship is a straight line. And there's a beauty in that simplicity. No acceleration, no deceleration. Just steady change. But then we discover quadratic polynomials, and things become more interesting. These are degree 2 polynomials. Now we have a squared term, in addition to our linear and constant terms. This is where curves enter the picture. A quadratic polynomial describes something that accelerates or decelerates. The classic example is a ball thrown into the air. When you throw a ball upward, gravity is constantly pulling it back down with increasing force. The position at any given moment isn't just linearly related to time. It follows a quadratic relationship. The polynomial that describes this motion has shaped human understanding of physics, engineering, and mathematics itself. Let me paint a picture of this for you. Imagine you're on a baseball field, and you watch a batter hit a ball. In the first quarter of a second, it rises to a certain height. In the next quarter of a second, it rises a bit more, but not as much. In the next quarter, it rises even less. For a moment, it's at the peak, moving either up, down, down. Then it starts coming down. First slowly, then faster and faster. This entire trajectory, from the moment the ball leaves the bat to the moment it's caught, or hits the ground, can be perfectly described by a single quadratic polynomial. Isn't that remarkable? One simple equation captures the entire dance of the ball through space. And here's something even more beautiful. The shape of this trajectory never changes, in a fundamental sense. Whether you're talking about a baseball, a basketball, or a stone thrown from a cliff, the shape is always parabolic. It's always the same graceful curve. The numbers change, but the form remains. That's because gravity acts consistently, and the mathematics that emerges from that consistent force is always a quadratic polynomial. Now, you might wonder, what about more complex situations? What if we need to describe something even more complicated than a thrown ball? Well, that's where cubic polynomials come in. These have a squared term and a cubed term. They can have more interesting shapes, with bumps and valleys. The degree 3 polynomial is the lowest degree that can have what we call inflection points, places where the curve changes from bending one way to bending another way. In the real world, cubic polynomials show up everywhere. They describe the way volumes scale with dimensions. They appear in the mathematics of manufacturing and design. If you're trying to figure out the optimal dimensions for a box that maximizes volume while minimizing surface area, you're working with cubic polynomials. Nature uses these shapes because they're efficient, because they balance forces in space in elegant ways. And then we go higher. Quartic polynomials, degree 4. Quintic polynomials, degree 5. As we go higher and higher, the polynomials can have more and more complex shapes, more valleys and peaks, more intricate behavior. But here's the thing that kept mathematicians humble. Even though you can make polynomials of arbitrarily high degree, the most common and most important ones in nature, and in human affairs tend to be fairly low degree. A quadratic captures falling objects. The cubic captures optimization problems. A quartic might describe the shape of a hanging chain, or the stress distribution in a beam. This is one of the secrets of mathematics that doesn't get discussed enough. The universe, for all its apparent complexity, seems to prefer simplicity at its core. The patterns that show up over and over are relatively simple polynomials. This isn't a coincidence. It's a hint that we're on the right track, that we're understanding something true about the fundamental structure of reality. Let me tell you about where polynomials truly shine, and that's in the realm of approximation. This might seem like a strange thing to emphasize, but it's actually one of the deepest and most powerful insights in all of mathematics. Here's the core idea. Any smooth curve, no matter how complicated, can be approximated as closely as you like by a polynomial. You just need to use a high enough degree. This is called Taylor's theorem, named after the mathematician Brooke Taylor, and it's absolutely fundamental. It means that polynomials are, in a very real sense, universal approximators. They're the mathematical equivalent of Lego blocks. You can build almost anything with them if you have enough pieces. Think about this practically. Suppose you have some curved shape that's really complicated. Maybe it's the shape of a wing on an airplane, or the curve of a river as it winds through the landscape. If you want to understand this shape, to calculate properties of it, to predict how it will behave under different conditions, you can't always use the exact equation. Maybe there isn't an exact equation. Maybe the shape was designed by hand, or emerged naturally from complex processes. But here's the magic. You can take measurements at various points along the curve. You can use those measurements to construct a polynomial that follows your shape very closely. The more measurements you take, the higher the degree of polynomial you need. But you can get as accurate as you want. And once you have a polynomial, you can do calculations with it. You can find its maximum and minimum points. You can calculate its slope at any location. You can predict how properties depending on the shape will change. This is how computers store complex shapes. When you watch an animated movie or play a video game, the beautiful curves you see aren't actually stored as pixels. They're stored as polynomials. Each curve is represented by a polynomial of some degree, and the computer uses that polynomial to generate the pixels at whatever resolution you're viewing them at. If you zoom in, it calculates more pixels from the polynomial. If you zoom out, it calculates fewer. The polynomial gives you the information you need at any level of detail. This same principle is used in manufacturing. When engineers design a part on a computer, they use polynomials to describe the surfaces. The polynomials are then passed to the machines that fabricate the parts. The machines follow the polynomial descriptions, creating physical objects of extraordinary precision. Without polynomials, modern manufacturing as we know it simply wouldn't exist. But the importance of polynomials goes even deeper than practical applications. They're important because they teach us something profound about the structure of mathematics itself. You see, in the 17th and 18th centuries, mathematicians discovered something that shook their understanding of the universe. They found that many physical laws, when expressed as equations, involved what's called a differential equation. These are equations that relate quantities to their rates of change. The canonical example is Newton's second law of motion. Force equals mass times acceleration. Acceleration is the rate of change of velocity, and velocity is the rate of change of position. So this one equation relates forces, which we can measure, to the motion that results. Now, solving these differential equations turned out to be related to polynomials in a surprising way. When you have certain types of differential equations, the solutions can be expressed as power series, which are essentially infinite polynomials. They're polynomials that go on forever, with terms of higher and higher degree. And these power series solutions to fundamental physical equations describe the behavior of systems throughout nature. The sine function, which describes oscillations and waves, can be expressed as an infinite power series. The exponential function, which describes growth and decay, is also a power series. The cosine function, the natural logarithm, even more exotic functions can all be expressed this way. So in some very real sense, all of calculus, which is the mathematics of change and motion, is built on foundations of polynomials and power series. Let me take you on a little journey through what this looks like in practice. Imagine you're trying to understand the motion of a pendulum. You have a weight hanging from a string, and you pull it back and release it. It swings back and forth in a rhythmic motion. If you measure the angle from vertical at different times, you'll notice that the motion is periodic. It repeats. If the angle is small, the motion of a pendulum can be described by a fairly simple polynomial equation. But the exact behavior involves something called the sine function. When you write down what a sine function is mathematically, one way to express it is as an infinite power series. The sine of an angle x equals x minus x cubed, divided by 6 plus x to the fifth divided by 120, and so on, with more and more terms. What this tells us is that even this fundamental function, this description of oscillatory motion, is built from polynomials. We can approximate the sine function with just the first term, and we get the angle itself. That's a pretty rough approximation. If we keep the first two terms, we get something much better. The more terms we include, the more accurate our approximation becomes. This is almost poetic when you think about it. Nature's fundamental behaviors, when expressed mathematically, emerge as infinite sums of polynomial terms. We get these beautiful series, these nested expressions of increasing complexity. And when we truncate them, when we keep just the first few terms, we capture the essential behavior. The first few terms of a power series give you the simple, dominant behavior. The later terms capture the fine details and corrections. This structure appears over and over in physics. The universe, it seems, likes to build complex behaviors from the sum of simpler polynomial pieces. It's not a bug in our mathematics. It's a feature of reality. Now let's talk about something that fascinated mathematicians for centuries. The roots of polynomials. A root is a value of the variable that makes the polynomial equal to 0. If you're looking at a graph of a polynomial, the roots are the points where the curve crosses the horizontal axis. For a linear polynomial, finding the root is trivial. If you have a polynomial that equals 0 at certain points, and you want to find where, you can just solve a simple equation. For quadratic polynomials, the situation is more interesting. There's a formula, the famous quadratic formula, that will tell you the roots. It's been known for centuries, and remains one of the most useful equations in mathematics. But here's where things get philosophically interesting. When you move beyond quadratics, to cubics and quartics, and higher degree polynomials, finding roots becomes dramatically harder. There are formulas for cubic and quartic polynomials, but they're complicated and unwieldy. And then comes a shocking revelation. For degree 5 and higher, there is no general formula using normal arithmetic operations and roots. This was proven in the 19th century by mathematicians like Évariste Galois and Niels Henrik Abel. It was a stunning result. It showed that even though polynomials of degree 5 definitely have roots, and we can approximate them numerically, there's no closed-form expression for those roots in general. This discovery marked a turning point in mathematics. It showed that not all problems have neat, tidy solutions. It was humbling, but it also opened up new mathematics. To understand why there were no formulas for degree 5 polynomials, mathematicians had to develop what's called group theory, and what's called Galois theory. These fields of mathematics have become absolutely central to modern physics and chemistry. We use them to understand symmetries in nature, to classify particles, to understand the structure of atoms. So, sometimes the boundaries of what we can't solve point us toward deeper truths. The study of polynomial roots also reveals something interesting about the relationship between algebra and geometry. The roots of a polynomial are the places where the polynomial equals 0. But you can think about polynomials in more dimensions. If you have a polynomial in 2 variables, the places where it equals 0 form a curve in 2-dimensional space. A polynomial in 3 variables defines a surface in 3-dimensional space. These geometric objects, called algebraic varieties, are fundamental objects of study in mathematics. They're beautiful, intricate, and deeply connected to the behavior of the polynomial itself. Let me shift gears a bit and talk about something that might seem completely different, but is actually deeply related to polynomials: the concept of continuity and smoothness. When we look at a polynomial, one of its most pleasing properties is that it's smooth. There are no sharp corners, no jumps, no sudden breaks. If you're drawing a polynomial, you can draw it with one continuous line without lifting your pen from the paper. This smoothness is important. It means that if you know the value of a polynomial at one point, you can make predictions about nearby values. It means small changes in the input lead to small changes in the output. This property, called continuity, is one of the foundations of calculus and real analysis. But here's something subtle. Not all continuous curves are polynomials. A polynomial is a very specific type of continuous curve. It has the additional property that its slope at any point can be calculated precisely. The slope changes smoothly as you move along the curve. This is what we call being differentiable. In fact, this is getting at one of the deep connections in mathematics. Polynomials are not just useful for describing nature, they're also the natural objects you get when you do calculus. When you take a derivative of a polynomial, you get another polynomial of lower degree. When you integrate a polynomial, you get a polynomial of higher degree, plus a constant. Let me explain what I mean by derivative, since it's such an important concept. A derivative measures how fast something is changing. If you have a polynomial that describes height as a function of time, the derivative tells you the velocity, how fast the height is changing. If you take the derivative of the velocity, you get the acceleration, how fast the velocity is changing. For a linear polynomial, the derivative is a constant. The rate of change is the same everywhere. For a quadratic polynomial, the derivative is linear. The rate of change itself changes at a constant rate. This is exactly what we see with objects under the influence of gravity. The velocity changes at a constant rate, which is the gravitational acceleration. When you take derivatives of higher degree polynomials, you get lower degree polynomials. The degree 5 polynomial has a degree 4 polynomial as its derivative, which has a degree 3 polynomial as its derivative, and so on. Eventually you reach a constant, and then the derivative of a constant is 0. This structure, where derivatives of polynomials are still polynomials, makes them perfect for the study of calculus. And calculus is the mathematics of continuous change, which is the mathematics that governs the physical universe as we understand it. Now I want to talk about something that might seem abstract, but is actually quite concrete. I want to talk about polynomial interpolation. This is the idea that if you have a set of points, you can find a polynomial that passes through all of them. Imagine you're a scientist, and you've measured some quantity at different times, or under different conditions. You've measured the temperature at different heights in the atmosphere, or you've measured the strength of a material under different stresses. You have a collection of data points, each one showing a relationship between two things. Now, you want to understand the relationship in between your measurements. What's the temperature at a height where you didn't measure? What would the material strength be, and a stress level you didn't test? You could guess, but it's better to fit a curve through your data points and use that curve to make predictions. A polynomial can do this. In fact, there's a beautiful theorem that says, given any collection of points, no two of which have the same horizontal coordinate, there exists a unique polynomial of degree, at most n-1, that passes through all n of the points. This is called Lagrange interpolation, and it's one of the most useful tools in applied mathematics. The process of finding this interpolating polynomial is elegant. You can use something called the Lagrange basis functions. For each data point, you construct a polynomial that equals 1 at that point and 0 at all the other points. Then you scale each polynomial by the vertical coordinate of its corresponding data point and add them all together. The result is a polynomial that passes through every data point. This might sound complicated, but the beauty is that it's systematic. You can do it by hand for a few points, or you can program a computer to do it for millions of points. The mathematics is the same, just scaled up. This technique is used throughout science. When you're using a computer to do calculations involving experimental data, one of the most common steps is polynomial interpolation. It's how scientists and engineers work with data that's been collected at discrete points, that actually represents a continuous phenomenon. Let me tell you about a particularly beautiful application of polynomials. Bezier curves. These are curves that are defined by polynomials, and they've become absolutely central to computer graphics and digital design. A Bezier curve is defined by a set of control points. You have a starting point, some points in between that influence the shape of the curve, and an ending point. The polynomial is then calculated such that it starts at the starting point, ends at the ending point, and is influenced by all the intermediate points in a particular way. The result is a smooth curve that's intuitive to work with. What makes Bezier curves so powerful is that they're defined by polynomials, which means you can manipulate them mathematically. You can calculate their properties, combine them, split them, rearrange them. But they're also intuitive to work with visually. You can grab a control point and drag it, and the curve updates smoothly and predictably. If you've ever used a drawing program like Adobe Illustrator or Photoshop, you've been working with Bezier curves. If you've watched an animated movie or played a modern video game, you've seen Bezier curves. When you print something on a modern printer, the fonts you see are often defined using Bezier curves. When you design a car or an airplane, or the furniture on a computer, you're probably using Bezier curves. Bezier curves are a beautiful example of how an abstract mathematical concept becomes practical when you understand it deeply. The polynomials that define them are usually cubic, meaning degree 3. They have enough flexibility to create interesting shapes, but not so much that they become difficult to work with. This balance, this finding of the sweet spot in the complexity, is characteristic of good mathematical design. Let me shift now to something that might seem surprising. I want to talk about how polynomials connect to something called the discrete or digital world. We often think of polynomials as describing smooth, continuous curves. But polynomials are also useful in the digital realm, where everything is discrete, made of individual ones and zeros. One application is an error correction. When you transmit digital information over a network, errors can happen. A bit can flip from 0 to 1, or vice versa. This is a real problem in communication, especially over noisy channels or over long distances. Polynomials help solve this. The idea is clever. You take your message, which is a sequence of bits, and you treat it as a polynomial. Each bit becomes the coefficient of a polynomial term. Then you compute some additional values from this polynomial, and send them along with your message. If some bits are corrupted during transmission, you can use the mathematical properties of polynomials to figure out which bits were changed and correct them. This is the basis of Reed-Solomon error correction codes, which are used in QR codes, in spacecraft communication, in data storage, and in countless other applications. Because of polynomials, we can transmit information reliably even when errors are occurring. It's a beautiful application of abstract mathematics to the very practical problem of keeping information intact. Another surprising application is in cryptography, the science of secret communication. Some of the most secure encryption methods use polynomials. The idea is that if you have a polynomial with certain properties, and someone only knows the output values, but not the polynomial itself, it's very hard for them to figure out what the polynomial is. This asymmetry, this difference between how easy it is to evaluate a polynomial and how hard it is to reverse engineer one, forms the basis of some cryptographic systems. Now let's return to something more fundamental. I want to talk about why polynomials are so special from a theoretical perspective. What makes them different from other types of functions? One key property is that polynomials are algebraic. This means they can be built up using only a finite number of additions, subtractions, and multiplications. You don't need square roots. You don't need trigonometric functions. You don't need logarithms. Just arithmetic. In some sense, polynomials are the most basic functions you can construct. This is important because it means polynomials have a particular kind of simplicity and purity. When a polynomial appears in a physical law or a mathematical proof, it's telling you something fundamental. It's saying that the underlying phenomenon can be understood using only the most basic arithmetic operations. The opposite of algebraic is transcendental. Functions like the sine function, the exponential function, the logarithm, these are transcendental. They require more sophisticated machinery to define. But as I mentioned earlier, they can be expressed as infinite sums of polynomial terms. So in a deep sense, even transcendental functions are built from polynomials. This hierarchy, where polynomials are the foundation and other functions are built from them, gives polynomials a kind of primacy in mathematics. They're not just convenient tools, they're fundamental objects that help us understand the structure of mathematics itself. Let me talk now about multivariate polynomials, polynomials that involve more than one variable. This takes us into richer mathematical territory. In one variable, a polynomial is a sum of terms, where each term is a number times the variable raised to a power. In two variables, say x and y, things get more interesting. Now a single term might be something like 5 times x squared times y to the third power, and a polynomial in two variables is a sum of such terms. What's remarkable is that the same principles apply. A two-variable polynomial describes a surface in three-dimensional space. When we set the polynomial equal to 0, we get a curve in the two-dimensional plane. These algebraic curves have been studied for centuries and reveal deep truths about mathematics. Some of the most famous curves in mathematics are algebraic curves defined by polynomials. An ellipse can be defined by a polynomial equation. A hyperbola can be. A circle is a special case of an ellipse, also defined by a polynomial. The curves that planetary orbits follow are conic sections, which are the curves you get from the zero set of degree 2 polynomials in two variables. When Johannes Kepler discovered that planets move in elliptical orbits, he was discovering that the shape of planetary motion is the shape defined by a degree 2 polynomial in two variables. Newton later explained why this was true, using his law of gravitation, but the mathematical fact remains. The universe chose ellipses as the paths for planets, and ellipses are defined by polynomials. This is one of the great mysteries of the cosmos. Why do the fundamental shapes that appear in nature correspond so closely to the shapes defined by relatively low-degree polynomials? Is it a coincidence? Or is it a hint that we're understanding something true and deep about the structure of reality? As we move to higher dimensions, the situation becomes even more intricate and interesting. A polynomial in three variables defines a surface in three-dimensional space. When we require the polynomial to equal 0, we get a two-dimensional surface embedded in three dimensions. These algebraic surfaces are objects of extraordinary beauty and complexity. Mathematicians study these objects by understanding their properties. How many connected pieces do they have? What holes or tunnels run through them? These topological properties, combined with the algebraic structure from the polynomial definition, reveal the geometric nature of these spaces. This field, called algebraic geometry, has become one of the most vibrant and important areas of modern mathematics. It connects algebra, geometry, topology, and analysis in ways that are both profound and beautiful. And at the heart of it all are polynomials. Let me tell you about something that might sound very abstract, but is actually quite concrete and practical. The Chinese remainder theorem, as it applies to polynomials. The original Chinese remainder theorem, which comes from ancient Chinese mathematics, tells you how to solve systems of linear equations under certain conditions. But mathematicians realize that the same idea applies to polynomials. The polynomial remainder theorem says that if you divide a polynomials by a linear polynomial, the remainder is a constant. Moreover, that constant is the value of the original polynomial evaluated at the root of the linear polynomial. This might sound technical, but it has practical applications. For instance, in digital signal processing, we often want to decompose a polynomial into simpler pieces. The remainder theorem and its generalizations help us do this. We can break a complex polynomial down into a sum of simpler polynomials, each of which is easier to work with. This decomposition is called partial fractions, and it's one of the most important techniques in calculus. When you're integrating a rational function, which is the quotient of two polynomials, You use partial fractions to break the rational function into a sum of simpler pieces that are easier to integrate. The fact that polynomials can be decomposed in this way is profound. It tells us that complexity in polynomials is always a kind of composed simplicity. You can always break it down into more fundamental pieces. This property is one of the reasons polynomials are so useful. They have this recursive, nested structure that makes them tractable. Now let me tell you about the theory of polynomial equations, and something called the fundamental theorem of algebra. This is one of the most important theorems in all of mathematics, and it says something quite remarkable. The theorem states that every polynomial of degree n, with complex coefficients, has exactly n roots, counting multiplicities, in the complex numbers. This is a completely non-obvious statement, and it took centuries of mathematical development to prove rigorously. What does it mean? Well, let's think about it in terms of the polynomial equations we solve. If you have a quadratic polynomial, the theorem tells you there are exactly 2 roots. You might know them, or they might be complex, but they're there. If you have a cubic polynomial, there are exactly 3 roots. A degree 100 polynomial has exactly 100 roots. This is profound because it tells us that polynomials are complete in a certain sense. They don't have any missing solutions if you're willing to accept complex numbers. And complex numbers, which combine real numbers with what are called imaginary numbers, turn out to be the natural home for polynomial roots. The discovery that complex numbers were the right place to look for roots was a turning point in mathematics. It meant that even though you might not be able to express the roots in real numbers, they definitely exist and have a precise mathematical meaning. This led to a deep understanding of the structure of equations and of mathematical systems in general. The fundamental theorem also connects polynomials to the complex plane, a two-dimensional space, where the horizontal axis represents the real part of a complex number, and the vertical axis represents the imaginary part. The polynomial can be viewed as a function from the complex plane to itself. Every point in the plane gets mapped to another point by the polynomial. The roots of the polynomial are exactly the points that map to 0. When you visualize this mapping, you can see something beautiful. The polynomial creates a kind of landscape on the complex plane, with peaks and valleys and ridges. The roots are the points at sea level, where the elevation is exactly 0. Let me now talk about something even more profound: the role of polynomials in the study of symmetry. In modern mathematics and physics, symmetry is understood through something called group theory, and groups, especially when they act on spaces, are intimately connected with polynomials. Consider the symmetries of a geometric object like a square. A square has certain symmetries. You can rotate it by 90 degrees, and it looks the same. You can reflect it across a vertical line, and it looks the same. These transformations form a group. And if you want to understand how this group acts on the plane containing the square, you can use polynomials. The polynomial equations that describe the points that remain unchanged under a symmetry operation are called invariant polynomials. They're the polynomials that tell you about the essential structure of the symmetry. By studying these invariant polynomials, mathematicians and physicists can understand the symmetries of nature. This is how we understand fundamental particles in physics. The standard model of particle physics is based on certain symmetries. These symmetries are described using group theory, and the groups act on spaces in ways that can be understood using polynomial equations. So when physicists describe the fundamental forces in particles of nature, they're really talking about abstract algebraic structures that are captured in part by polynomials. The connection between symmetry and polynomials goes back further than modern physics. Ancient mathematicians studying the geometry of regular polygons were actually studying symmetries, and those symmetries can be captured by polynomial equations. The regular pentagon, for instance, is related to a famous polynomial equation that involves what's called the golden ratio. Let me tell you about that, because it's a beautiful example of how polynomials capture deep mathematical truths. The golden ratio is a number that appears over and over in nature and in geometry. It's often represented by the Greek letter phi. The golden ratio has the special property that if you take 1 plus the reciprocal of the golden ratio, you get the golden ratio back. This might sound circular, but it means the golden ratio satisfies a particular polynomial equation. The variable squared minus the variable, minus 1 equals 0. When you solve this quadratic polynomial, you get the golden ratio, which is approximately 1.618. This number has fascinated mathematicians for centuries. It appears in the proportions of the human face that we find beautiful. It appears in the spirals of shells. It appears in the branching of trees. And it's defined by a simple quadratic polynomial. Why does this number appear so often? Part of the reason is that it's the natural solution to certain optimization problems. When you have a rectangle, and you cut off a square from it, The remaining rectangle has the same proportions as the original rectangle, if and only if the rectangle has the golden ratio as its aspect ratio. This self-similar property, captured by the polynomial equation, seems to be something that nature finds efficient and uses repeatedly. Now let me expand on something that's crucial to understanding why polynomials matter so much: their role in the theory of functions and approximation. One of the central insights of mathematics is that functions, in general, are very complicated objects. But certain simple functions, like polynomials, are much easier to work with. Because of this, mathematicians have developed ways to approximate complicated functions using polynomials. The most famous such result is the Weierstrass approximation theorem. This theorem, proved by Karl Weierstrass in the 1870s, says that any continuous function on a closed interval can be approximated polynomial. You might need a high-degree polynomial, but it's always possible. What does this mean in practice? Suppose you have some complicated function that you don't have a formula for. Maybe you have a physical system, and you've measured its output at many different inputs. You want to understand this relationship mathematically. The Weierstrass theorem tells you that you can always find a polynomial that matches your data to any desired level of accuracy. This is why polynomials are so useful in science and engineering. You don't need to find the exact mathematical formula for a physical law. You just need to find a polynomial that matches your observations. And you know that such a polynomial exists. There are actually many ways to find such an approximating polynomial. One way is through something called polynomial regression, where you fit a polynomial to data points, using a technique called least squares. You choose the polynomial that minimizes the total squared error between the polynomial and the data points. This is a well-defined optimization problem with a unique solution, and it's one of the most practical applications of polynomials in data science. Another way is through Taylor series, which I mentioned earlier. If you know the function and its derivatives at a single point, you can write down a polynomial that approximates the function near that point. The polynomial captures the behavior of the function near that point, with the accuracy improving as you include more terms. These approximation techniques are the foundation of much of scientific computation. When a computer calculates the sine of an angle, or the square root of a number, or the logarithm of a value, it's usually doing so by evaluating a polynomial that approximates the function to the required accuracy. The polynomial is fast to evaluate, so the computer can do millions of them per second. Let me talk now about a question that might have been in the back of your mind. Why do we care so much about finding the roots of polynomials? What's so important about knowing where a polynomial equals zero? In mathematics and physics, the roots of polynomial equations tell you about equilibrium states, boundary conditions, and singularities. In engineering, finding the roots of the polynomial might tell you the frequencies at which a structure will resonate, or the stresses at which a material will fail. For instance, if you're building a bridge, you want to know the natural frequencies of vibration of the structure. These are determined by the roots of a polynomial equation related to the mass and stiffness of the bridge. If environmental conditions like wind excite the bridge at one of these frequencies, the bridge will resonate and could potentially fail. So finding these resonant frequencies, which means finding the roots of certain polynomials, is critical to safety. In electrical engineering, the stability of a control system is determined by the roots of the characteristic polynomial of the system. If all the roots are in a certain region of the complex plane, the system is stable. If any roots are outside that region, the system is unstable. So the stability of an aircraft, a power grid, or a robot depends on the roots of polynomials. In physics, the energy levels of an atom are the eigenvalues of the Hamiltonian operator, which is related to the roots of certain polynomial equations derived from the quantum mechanical description of the system. Understanding the energy levels of atoms is crucial to understanding chemistry and the properties of materials. So the question, where are the roots of this polynomial, is not some abstract mathematical puzzle. It's a very practical question, whose answer often has real-world consequences. Now, I want to tell you about something that bridges the gap between polynomials and some of the deepest mathematics in the world: the concept of polynomial degree and its relationship to complexity. In general, the degree of a polynomial is a measure of its complexity. The degree 1 polynomial is linear, simple. The degree 2 polynomial is quadratic, more complex, but still very manageable. As the degree increases, the polynomial becomes more intricate, with more potential for interesting behavior. But here's something subtle. In many areas of mathematics and physics, the degree of the polynomial that shows up is often quite low. Quadratic and cubic polynomials are by far the most common. Degree 4 polynomials are not uncommon, but degree 10 or higher polynomials are rare in fundamental applications. Why is this? One theory is that nature has a kind of economy. It tends to use the simplest structures that can capture the necessary behavior. A degree 2 polynomial can describe the motion of falling objects under constant gravity. You don't need a degree 10 polynomial for that. The degree 3 polynomial can describe many optimization problems. A degree 4 polynomial can describe the shape of hanging cables and chains. This economy of nature, this preference for simplicity, is reflected in the polynomials that show up. It's as if the universe is written in a language where the most common words are the simplest ones. There's a deeper principle here, related to something called the principle of least action. In physics, many systems evolve in a way that minimizes some quantity, called the action. The equations of motion that result from this principle, when analyzed, often involves polynomials of low degree. It's not a coincidence. It's a feature of the principle itself. Let me now tell you about something that's been a subject of mathematical research for centuries. The shapes of polynomials and their behavior. When you graph a polynomial, you get a curve. This curve has certain characteristics. It might have peaks and valleys. It might increase monotonically, always going upward. It might change direction multiple times. The number and location of these peaks and valleys are determined by the degree of the polynomial and the coefficients. For a degree 2 polynomial, also called a parabola, there's exactly one peak or one valley. It's symmetric. For a degree 3 polynomial, there can be 0 or 2 peaks and valleys, depending on the coefficients. For a degree 4 polynomial, there can be 0, 1, 2, or 3 peaks and valleys. In general, a degree n polynomial can have its most of -1 peaks and valleys. This is because the peaks and valleys occur where the derivative of the polynomial equals 0. The derivative of a degree n polynomial is a degree n-1 polynomial. And a degree n-1 polynomial can have at most n-1 roots. So there can be at most n-1 peaks and valleys. This relationship between the polynomial and its derivative, captured by the calculus, tells us something deep about the shape of the polynomial. The shape isn't arbitrary, it's constrained by the degree. Understanding these shape constraints is useful. If you're trying to fit a polynomial to data, you need to choose the degree carefully. If you choose too low a degree, the polynomial can't capture the actual behavior. If you choose too high a degree, the polynomial might have unnecessary peaks and valleys, and it will be less stable and less useful for making predictions. Now, let me tell you about a concept that's related to the shape of polynomials, but goes deeper. The concept of monotonicity and convexity. The polynomial is monotonically increasing on an interval if it's always going upward on that interval. Mathematically, this means its derivative is always positive. A polynomial is convex if it curves upward, which means its second derivative is always positive. These properties are related to the roots of the polynomial and its derivatives. Understanding where a polynomial is monotonic and where it's convex helps you understand its overall shape and behavior. It helps you find the maximum and minimum values. It helps you understand how the polynomial changes as you move along its domain. In optimization problems, which are everywhere at applied mathematics and science, the goal is often to find a maximum or minimum of some quantity. If that quantity is a polynomial, or if it can be approximated by a polynomial, then understanding its monotonicity and convexity is crucial. These properties tell you where the maximum or minimum must be. For instance, in machine learning, many optimization problems involve finding the minimum of an error function. If that error function can be approximated by a polynomial, or if it's convex, then mathematicians and computer scientists know that there are efficient algorithms for finding the minimum. The shape of the polynomial, captured by concepts like monotonicity and convexity, determines the difficulty and feasibility of the optimization problem. Let me shift now to something that might seem to have nothing to do with polynomials, but is actually deeply connected. Probability and statistics. In statistics, when you're trying to understand a dataset, one of the first things you do is compute summary statistics like the mean and the variance. But if you want to go deeper, if you want to understand the entire distribution of the data, you might use something called moments. The moments of a distribution are defined using powers of the variable. The first moment is the mean. The second moment is related to the variance. The third moment is related to skewness. The fourth moment is related to kurtosis. And so on. Now, if you know all the moments, reconstruct a distribution completely. And the way you reconstruct it is by summing up terms that involve powers of the variable, weighted by the moments. This is exactly like constructing a polynomial. So in some sense, probability distributions are represented by infinite polynomials, or power series. This connection between polynomials and probability is not coincidental. It's a deep part of the structure of mathematics. The techniques for analyzing polynomials can be applied to analyzing probability distributions. And conversely, probabilistic thinking can help us understand polynomials. For instance, if you have a polynomial with random coefficients, what's the probability that it has a root in a certain region? This is a question that statisticians and mathematicians have studied. The answer depends on the distribution of the coefficients and involves probabilistic techniques applied to polynomials. In modern machine learning and statistics, this connection between polynomials and probability is explicit. Many learning algorithms work by finding a polynomial that fits the data in a probabilistic sense. The polynomial is viewed as a model of the underlying process that generated the data. Understanding the polynomial tells you about the probabilistic structure of the data. Let me tell you about the history of polynomials more deeply, because understanding how humans discovered and developed this concept is part of understanding why they're so important. The story of polynomials goes back to the ancient Babylonians, over 3,000 years ago. They had methods for solving quadratic equations, though they didn't express them as polynomials. They wrote their mathematics in words or in geometric forms, not in the symbolic language we use today. The ancient Greeks advanced this further. Euclid, in his Elements, developed geometric methods for solving certain types of polynomial equations. The problem of doubling the cube, one of the famous unsolved problems of ancient geometry, is really a problem about finding the roots of a cubic polynomial. The Greeks couldn't solve it, and eventually it was proven that it's impossible using only compass and straightedge. But the search for the solution led to important discoveries in algebra. In the Islamic Golden Age, mathematicians made tremendous progress. Al-Khwarizmi developed systematic methods for solving quadratic equations. His work, translated into Latin, gave us the word algorithm. He also worked with polynomials, though he called them by different names and expressed them differently. The next major breakthrough came in the Renaissance in Italy. Mathematicians like Girolamo Cardano and Nicola Tartaglia developed formulas for solving cubic and quartic polynomial equations. These formulas are complicated, but they exist. The solutions can be expressed in terms of arithmetic operations and roots. This was a tremendous achievement. But then something surprising happened. Mathematicians tried to find similar formulas for degree 5 and higher polynomials. For centuries they failed. They tried different approaches, different techniques, but no general formula emerged. This puzzled them. For polynomials of degree 2, 3, and 4, there were formulas. Why not for degree 5? The answer came in the 19th century from mathematicians like Évariste Galois and Niels Abel. They proved that no general formula exists for degree 5 and higher polynomials. But in doing so, they created a beautiful new branch of mathematics called Galois theory. They showed that the question, can we solve this polynomial equation with a formula, is equivalent to a question about the symmetries of the polynomial. These symmetries form what's called the Galois group. If the Galois group has certain properties, the polynomial is solvable. If not, it's not. This was a turning point. It showed that not all problems can be solved by finding a formula, but it also showed that even unsolvable problems have structure. You can understand them deeply, even if you can't express the solutions with a simple formula. The development of complex numbers was another crucial development in the history of polynomials. For centuries, mathematicians were uncomfortable with the square roots of negative numbers. They called them imaginary, but gradually they realized that these imaginary numbers were actually very real and very useful. They allowed you to solve polynomial equations that had no real solutions, and they gave the fundamental theorem of algebra a home. Polynomials have roots in the complex numbers, even if they don't in the real numbers. In the 20th century, polynomials became central to the emerging field of computer science. Because polynomials are easy to evaluate using simple arithmetic, they were perfect for computers. The idea that you could represent any continuous function as a polynomial, or as a sum of polynomials, meant you could do function evaluation on a computer. This made scientific computing possible. And in the modern era, polynomials have become central to cryptography, error correction, signal processing, machine learning, and countless other fields. They're more important to technology and science than ever before. Let me tell you about a modern application that ties together many of the themes we've discussed. Neural networks. A neural network is a mathematical model inspired by the brain. It consists of layers of interconnected nodes. Each node applies some operation to its inputs and produces an output. If you chain together many of these simple operations, you can create a very complex function that can learn from data. Now, here's where polynomials come in. Some neural networks are actually implementing polynomial operations. Each neuron applies what's called an activation function to a weighted sum of its inputs. If the activation function is a polynomial, then the neuron is implementing a polynomial operation. By chaining together these polynomial operations, the neural network is building up a more complex polynomial. This observation has led to a new way of thinking about machine learning. Some of the most successful neural networks are, in a sense, approximating the data with high-degree polynomials. They're finding polynomial relationships in the data and using those to make predictions. Understanding this polynomial structure helps explain why neural networks work so well. It connects machine learning to the fundamental property of polynomials, that they can approximate any smooth function. If a neural network is building up a polynomial approximation to the underlying function that generated the data, then it's leveraging a fundamental property of mathematics to achieve its goals. Let me now talk about something abstract but beautiful. Polynomial rings. In modern abstract algebra, mathematicians study objects called rings, which have certain properties. The ring is a set with two operations, addition and multiplication, that satisfy certain axioms. One of the most important examples of a ring is the set of all polynomials with coefficients from some number system, like the real numbers or the integers. You can add two polynomials together to get another polynomial. You can multiply two polynomials together to get another polynomial. These operations satisfy the properties that define a ring. What's remarkable is that the theory of polynomial rings connects to deep areas of mathematics. If you study the structure of polynomial rings, you learn about ideals, factorization, and other concepts that appear throughout mathematics and physics. For instance, the concept of an ideal in a polynomial ring is related to the concept of symmetries and invariance. The ideals of a polynomial ring can be described by generating sets of polynomials. This connects to the topic of Grobner bases, which are special sets of polynomials with nice computational properties. Grobner bases are used in computer algebra systems to solve systems of polynomial equations. This is concrete mathematics with applications. When you use a computer algebra system like Mathematica or Sage, and you ask it to solve a system of polynomial equations, it's using Grobner bases under the hood. The mathematics of polynomial rings, developed in the abstract and general setting, becomes practical when you try to compute things. Let me tell you about one more connection between polynomials and something deep in mathematics: the relationship to topology and homology. Topology is the study of properties of spaces that are preserved under continuous deformations. Homology is a tool from topology that measures the presence of holes and cycles in a space. These are abstract concepts, but they're fundamental to modern mathematics. Now here's the surprising connection. Algebraic varieties, which are the sets defined by polynomial equations, are topological spaces. They have topological properties. The polynomial structure on these spaces can be used to compute their homology. This is the content of algebraic topology, a field that brings together algebra and topology. Algebraic varieties defined by polynomials are spaces that you can study topologically. The topology reveals information about the variety, and the algebra, captured by the polynomial equations, constrains the topology. This interplay between algebra and topology, mediated by polynomials, is one of the deepest and most beautiful areas of mathematics. It's far beyond what we can explore in detail here, but the fact that polynomials bridge these different worlds of mathematics is yet another indication of their fundamental importance. Now, as we're nearing the end of our exploration, let me reflect on the central question that motivated our journey. Why are polynomials the secret to the universe? I think the answer involves several layers. First, polynomials are simple. They're built from the most basic arithmetic operations, multiplication and addition. Because they're simple, they're easy to analyze. We understand polynomials deeply. We can find their roots, calculate their derivatives, understand their behavior. Second, polynomials are universal. Because of the Weierstrass approximation theorem and related results, any smooth function can be approximated by polynomials. This means polynomials are universal approximators. Whatever smooth behavior you're trying to describe, you can do it with polynomials if you're willing to use a high enough degree. Third, polynomials connect to calculus naturally. The derivative of a polynomial is a polynomial. The integral of a polynomial is a polynomial. This means polynomials fit naturally into the framework of calculus, the mathematics of change and motion. Fourth, polynomials connect to fundamental physics. The laws of motion, written as differential equations, have solutions that are often polynomials or sums of polynomials. The shapes of orbits, the patterns of waves, the behavior of electrical fields, all of these are captured by polynomials or functions built from polynomials. Fifth, Polynomials have a wonderful recursive structure. You can factor them, decompose them, analyze them, breaking them down into simpler pieces. This recursive structure is mirrored in the recursive structure of nature, where complex systems are built from simpler components. Sixth, polynomials are computable. Computers can work with polynomials very efficiently. Evaluating a polynomial just requires multiplication and addition, operations that computers are fast at. This computational tractability means polynomials are perfect for numerical mathematics and scientific computing. Seventh, and perhaps most importantly, polynomials are everywhere. In physics, in engineering, in biology, in economics, in signal processing, in machine learning. The success of mathematical modeling, the fact that we can describe natural phenomena with mathematics at all, seems to rest fundamentally on polynomials. Why this is the case is a deep philosophical question. Is it because nature really is fundamentally polynomial? Or is it because our minds are adapted to understand and use polynomial thinking, and we've built our mathematical frameworks around them? I think the answer is a bit of both. Some aspects of nature are fundamentally polynomial, as we see when we derive physical laws from first principles. But we've also chosen to develop mathematics around polynomials, because they're so useful, and because our minds find them intuitive. The key insight is that there's a feedback loop. We discover that nature follows polynomial relationships. We develop mathematics around polynomials because they're useful. This developed mathematics helps us discover more about nature. As our understanding grows, we keep finding polynomials at the foundation. Let me tell you about something poetic, the aesthetic appeal of polynomials. Many mathematicians talk about the beauty of polynomials, the elegance of the theorems about them, the satisfaction of working with them. There's something beautiful about a parabola, the curve defined by a quadratic polynomial. It's symmetric. It has a perfect peak or valley. It's smooth and continuous. Architects and artists have used parabolic shapes for centuries, because they're beautiful. There's something beautiful about the way the roots of a polynomial relate to the shape of its graph. If you know where the polynomial crosses the horizontal axis, you know something fundamental about its shape. The roots are like the skeleton of the polynomial, the structural framework on which everything else is built. There's something beautiful about the way derivatives work with polynomials. The derivative of a polynomial tells you its rate of change at every point. The derivative is itself a polynomial of lower degree. It's like you're peeling away layers, revealing the simpler structures underneath. There's something beautiful about the way polynomials fit together in Taylor series. A complicated function can be expressed as an infinite sum of polynomial terms, each contributing something to the whole. It's like watching the painting be built up stroke by stroke, each stroke adding detail and beauty. The beauty of mathematics, of which polynomials are a central part, is not separate from the truth of mathematics. The fact that something is beautiful often signals that you've understood something deeply. The fact that polynomials are beautiful means we're understanding something true and fundamental. As we wrap up our exploration, let me share some thoughts about the future of polynomials in mathematics and science. In quantum computing, which is emerging as a revolutionary technology, polynomials play a role. Quantum algorithms are often analyzed in terms of their polynomial complexity, and some quantum algorithms work by finding roots of certain polynomial functions in quantum systems. In artificial intelligence and machine learning, the connections to polynomials are becoming clearer and more explicit. Researchers are developing new neural network architectures that explicitly work with polynomial basis functions. This brings together the computational power of neural networks with the mathematical understanding we have of polynomials. In pure mathematics, the study of algebraic variety, which are defined by polynomial equations, continues to be a frontier. The Langlands program, one of the most ambitious programs in modern mathematics, connects polynomials and Galois theory to representation theory and harmonic analysis. If successful, it will reveal deep connections between different areas of mathematics. In cryptography, as quantum computers threaten to break current encryption methods, polynomials are becoming even more important. Post-quantum cryptography algorithms often rely on the hardness of certain polynomial problems, like finding roots of high-degree polynomials over finite fields. The future of polynomials is bright, because the future of science and technology rests on our ability to understand and model the world mathematically. And polynomials, it seems, will always be at the foundation of that understanding. Let me leave you with a final thought. The ancient mathematicians didn't know about polynomials explicitly. The medieval Islamic mathematicians were beginning to work with polynomial-like ideas. The Renaissance mathematicians discovered formulas for polynomial roots. The modern mathematicians developed the theory of polynomials. And now, we live in an age where polynomials are absolutely central to every technological advance. What did ancient people know about polynomials that we've forgotten? What did they notice in nature that led them to develop the mathematical language of polynomials? Perhaps they noticed the curves of arches. Perhaps they noticed the paths of projectiles. Perhaps they noticed the spirals in shells and flowers. They couldn't express it mathematically as we do, but they understood, at some level, that there was a beautiful mathematical order to these things. We've developed the language to express that order precisely, and that language is, in large part, the language of polynomials. We've learned to hear the universe speaking in the grammar of polynomials, and as we listen more carefully, we understand more deeply. The secret to the universe, if there is one, seems to be that it's fundamentally simple. Not simple in the sense that it's easy to understand, but simple in the sense that it's built from basic components. And those components are polynomials. Add them together and you get complexity, but the basic building blocks remain simple. This is what gives us hope as mathematicians and scientists. No matter how complex the problem, no matter how intricate the system, if we can understand it mathematically, we can probably capture its essence using polynomials. They might be high-degree polynomials. They might be in many variables, but the fundamental structure is there, and once we've captured something in polynomial form, we can manipulate it, analyze it, compute with it, and ultimately, understand it. That's the power of polynomials. That's why they're secret to the universe. Not because they contain all knowledge, but because they're a universal language for describing the most important patterns and relationships in nature.